In this lesson, we're going to continue on from the geometric sequence that we learned from the last lesson and then apply it to geometric series. So we're going to investigate what a fractal is first. So a fractal is a geometric figure that is created by repeating a given pattern numerous times on the original figure. The repetitions are called iterations, and the repeated pattern may be larger or smaller than the original figure. This means the fractal may be divergent or convergent. The following diagram shows a fractal tree. So that we have the first iteration here, which looks like it's just one branch. Then iteration 2, we have 2 new branches on top of that. Iteration 3, we have iteration 2 in here, which is this part of the picture, and then we added 4 more branches. Now we're going to draw iteration 4. Iteration 4 is going to include iteration 3, so that's what I'm going to start off by drawing. Which looks something like this. And then now on each end of the branch, I'm going to add 2 more branches, because in iteration 2 we added 2 branches, in iteration 3 we added 2 on each branch. So then I'm going to add 2 branches on that end, another 2 here, another 2 here, and another 2 here. This will be iteration 4. Go ahead and draw iteration 5 and then check to see what mine looks like afterwards. So here I have iteration 4 drawn first for my iteration 5. Now I'm going to add 2 branches on the end of each. And that's what it's going to look like for iteration 5. Let's try to record what we've done here in a table of values. So for iteration 1, we have 1 branch. For iteration 2, we have 2 new branches. For iteration 3, we added 4 new branches. And if you look back on iteration 4, we added 8 new branches, and then iteration 5, we've got 16 new branches. Now we're going to decide whether a geometric sequence has been generated for the number of new branches formed at each stage. And if a geometric sequence has been generated, we're going to state the first term, the common ratio, and the general term. So let's again look at our table of values here and compare the number of new branches. So if going from 1 to 2, the only way for us to get from 1 to 2 is if we multiply by 2 here. From 2 to 4, same sort of thing. 4 to 8, have to multiply 4 by 2 to get 8, and then so on. So it looks like we do have a geometric sequence. And this would be r is equal to 2. Our first term, t1, is 1 for the first iteration, and the number of branches we had is 1. And if I want to find the general term, we're going to use the same formula from our last lesson, which is t1 multiplied by r to the power of n minus 1. So that would be for your general term. So this is a geometric sequence. I'm going to answer this as a yes. The second part, we're going to find and describe a strategy we could use to determine the number of total branches formed by the end of iteration 5. In this case, we can use the same formula from the last lesson. Tn is equal to t1 times r to the power of n minus 1. And if you want to find iteration 5, that would just be t5, the first term, times r, which is 2, in this case, to the power of 5 minus 1. And if we did this calculation, that's 2 to the power of 4, which is 16, and that's exactly what we had in our chart. And would this be a suitable strategy to find the total number of branches up to iteration 100? Yes. Now drawing it would not be feasible, but using this formula would be. So that means we're looking for t of 100, first term times r, which is 2, to the power of 100 minus 1, which is 99. So your last or term here of 100 is going to be 2 to the power of 99. I'm going to leave it like that because if you try to plug in the calculator, it's going to be a huge number that we can't even record properly. So, finding the total number of branches on the fractal tree on the last page is an example of a geometric series. Remember, a series is a sum of some sort of sequence. So a geometric series then is the sum of the terms of a geometric sequence. For example, 6, 12, 24, and 48 is a geometric sequence, but if we add up the terms together, that is a geometric series. Then so T1 is S1, which is 6. S2 is adding the first two terms together, which is 6 plus 12. So S2 is 18. S3 is T1 plus T2 plus T3, which is 6 plus 12 plus 24, and that's 42. And this is the formula we're going to use to find the sum of a geometric series, where T1 is the first term, R is your common ratio, Sn is the sum of the first n terms, and n is the number of terms. So we're going to find the sum of the first 12 terms of the geometric series, 3 plus 12 plus 48 plus 192. So I'm going to need T1, and that's the first term, which is 3. Then I need to find R, which is our common ratio. So to get from 3 to 12, I would need to multiply 3 by 4 to get 12. And I would need to multiply 12 by 4 to get 48. So 4 is our common ratio. And then it ends the number of terms. We're looking at the first 12 terms of this geometric series. Now I'm going to write our formula down. So Sn in this case is S12. And then the next part of the formula says T1, so that's 3. Then 1 minus R is 4 to the power of 12, all over 1 minus R. So you're going to do 1 minus 4 to the power of 12 in your calculator first, then multiply it by 3, and then divide it by -3. So you're going to get 16,777,215 as the sum of the first 12 terms in this series. Moving on to example 2, the sum of the first 14 terms of the geometric series is 16,383, and we know the common ratio is -2. We want to find the very first term. So in this case, we know what S14 is. And we know what R is, and we're looking for T1. So I'm going to write down our formula, and then we're going to fill in what we know and solve for T1. Okay, so Sn in this case is S14. We replace Sn with 16,383. T1's what we're looking for, so I'm going to leave that alone. R is -2. N is 14, because we're looking at the first 14 terms, all over 1 minus -2. Now simplify our denominator first, which is going to be 3. And I'm also going to find what -2 to the power of 14 is, and is 16,384, all over 3. I'm going to multiply both sides by 3. And I'm going to simplify what's in the bracket, so that's 1 minus 16,384, which is -16,383. Then we're going to divide both sides by -16,383, so T1 then is -3. Let's look at example 3. We're going to calculate the sum of this geometric series. So T1 is -3, R is 5, because to get from -3 to -15, I have to multiply this by 5. Same thing for here, -15 to get to -75, I have to multiply it by 5. N is something we actually don't know. We know the last term though, we know what Tn is. So we need to have n in order to use the sum formula. So the first thing we're going to do is find n. And to find n, we're going to use the formula we learned in the last lesson. So I'm going to fill in what we know. We know what Tn is. We know what T1 is. We also know what R is, and I'm going to leave the n alone because that's what we're looking for. Next step, I'm going to divide both sides by -3. So we're left with 5 to the power of n minus 1 here. I'm going to rewrite 15,625 with a base of 5. So it'll be 5 to the power of something. You can play around in your calculator for that. You're going to find that this will be equivalent to 5 to the power of 6. And now we can just focus on the exponents. So 6 is equal to n minus 1. That means n is going to be 7. Now that we know what n is, now I can use our formula to find the sum of the first 7 terms. So we're going to put T1 here, 1 minus R to the power of n all over 1 minus R. So 1 minus 5 to the power of 7 is negative 78,124. 1 minus 5 is -4. Then lastly, we're going to multiply -3 and -78,124 and then divide it by -4. You're going to get -58,593. And that is the sum of this geometric series. One more question. This is a word problem question. So a person takes tablets to cure a chest infection. Each tablet contains 500 milligrams of an antibiotic. About 15% of the mass of the antibiotic remains in the body when the next tablet is taken. Determine the mass of an antibiotic in the body after each number of tablets. So let's try to break down what is in this example, because we've been given quite a bit of information. So each tablet contains 500 milligrams. So I'm just going to say T1 then is 500 milligrams. We also have been given 15% of the mass of the antibiotic remains in the body when the next tablet is taken. So that means R, change this to a decimal is 0.15 because I'll divide by 100. But I know R is not just 0.15 because we know that there's going to be more antibiotic that's going to remain in your system if you take it more often. So I'm going to put a 1 in here because we're going to include this 500 milligrams afterwards. And in this case, we're looking at 3 tablets, so n is 3. So again, your R is what remains and the next tablet. So that means this 15% is what is remained from the last tablet, and the 1 in the front is the full next tablet, which is 500 milligrams. So because they're asking us to find the mass of the antibiotic in the body, we're not looking for the sum or the total of this entire series. So I'm looking for the sequence. It's particularly 1 tablet, 2 tablets, and 3 tablets. So I'm looking for T1, T2, and T3. So we know what T1 is. T1 is 500, and this would be 1 tablet. T2 represents 2 tablets. And you're going to find it by multiplying 500 by 1.15, and you're going to get 575. Which makes sense because 75 milligrams is what's going to remain from the first tablet, and then you get the 500 milligrams from the second tablet. Then lastly for T3, which is what we want, the 3 tablets, I'm going to multiply 575 by 1.15, and we're going to get 586.25 milligrams. And this is what we're looking for. This is the mass of the antibiotic in the body after 3 tablets. Moving on to the last part of this question, we want to look for the same sort of thing, but for 10 tablets. I'm not going to go through the same sort of method I've been using because it takes too long. Equivalently, I can just find what T10 is, and that will give us the mass of the antibiotic in the body after 10 tablets. So to calculate this, we're going to use our geometric sequence. So that's T1 multiplied by R to the power of n, which is 10 in this case, minus 1. And then that's 500 multiplied by 1.15 to the power of 9. So I'm going to do 1.15 to the power of 9 in the calculator first, then multiply it by 500. We're going to get 1,758.94 milligrams.